and record. All right, it should be recording.
Awesome.
So, hello everyone. Unfortunately, the polling feature on Zoom isn't working, so you're gonna have to respond to this amazing poll simply over the Zoom chat, but it is what it is.
Please let us know, because this is a very polarizing question. Oh, okay. So we've got one for Star Trek and one for the Mongol Overlord, 2 for the Mongol Overlord, 3 for the Mongol, 2 still.
Sal has gotten me through half my education.
Okay. Wow, a lot of Genghis Khans. But okay, we're equaling Genghis Khans and the Khan Academy Khans. Thomas, what about you?
Yeah, I think I would go. With. Why is this not working? There you go. I think I would go with Khan Academy as well.
I would have to agree with you. Yeah, it's really close. It's really close. I like
his teaching style is better than Genghis Khan's, definitely.
Well, I think more people learn their lesson with Genghis Khan than some.
Well, it depends, right? Depends on the lesson. There's only one with Genghis.
Yeah, he taught one lesson, but he taught it pretty well.
He did.
It'd be interesting to see a teacher that went in the middle, where he did nice like virtual drawing instructions on calculus, and then also threatened to burn you if you didn't do your homework.
The marauding Mongol hordes of math teachers.
All right, we'll probably just give it one more minute and then maybe get started.
Yeah, I would say so.
If you change the Zoom link, do we have the new Zoom link on the Facebook page?
No, this was like us doing this. If we had figured it out like maybe 5 minutes before, we wouldn't have changed the Zoom link. But thank you, Andre. Yeah, this was an unfortunate technical hiccup, but thankfully it happened now, so it doesn't happen in the future when it's I mean, this is a pretty big event, but I mean, for another big event.
When someone more important shows up, is what you're saying.
I was gonna say when someone more important shows up, but I don't think we're gonna have someone more important to be able to show up for a while. We've peaked.
Okay, it is 7:05, so maybe we should go ahead and get started.
I think I'd agree. So, all right, everyone, how's it going? Welcome to the Quantum Computing and Industry Workshop. We've got hosts Thomas and I, and our special guest Sebastian, who we will formally introduce later. So let's talk just a little bit about what QC is. A lot of you in here have been to some of the other workshops, but for those of you that haven't, and for those of you that might be watching the recording, let's just go over a little about what it is. So what makes it different from classical computing? Well, with classical computing, you've got binary states, so ones and zeros with on and off with the transistors. That's what we use now, and that's what we've been using primarily. So quantum computing instead uses qubits. So it's a superposition of states rather than one state. So the Bloch sphere, still haven't got that pronunciation now. It essentially is a representation of all the possible states it can be in. And we've got the entanglement of the particles. So it allows us to basically store much more data. It's sort of like we have more, the entire system's in RAM. It's a lot of very fast data, but it's not really long term. But it allows for a lot of faster searching algorithms and faster prime factoring. We're going to talk about that slightly on the next slide. But it is a huge improvement, not necessarily something that we can use for all purposes, but it is definitely going to improve a lot of things. Like, for example, Thomas, would you like to talk about the usage?
Yeah, so there's a multitude of different ways in which quantum computing can help. We just have a few listed here. The first and the last one, breaking RSA encryption sort of goes along with the perfect secure end-to-end encryption, because luckily, even though quantum computing will completely nullify any sort of protection you have over the internet, it will also solve its own problem with perfect protection. To me, the most interesting use for quantum computing, though, is in the quantum chemistry, which will allow you to simulate molecules and reactions much larger than we can now, simply because those sorts of things exponentially increase in difficulty as you increase the size and number of particles. So that's what I'm super excited for with quantum computing.
All righty. So let's just a little bit of a brief overview. So we're going to start off with the companies that are involved in QC, the big ones, and sort of what positions they're looking for right now. And then we're going to kind of give a brief overview of what some QC positions might be, and then what qualifications you might have for those specific positions. We're going to kind of summarize those into general, if you wanted to get into this general position, this is the qualifications you need. And then we're going to be having a I'll fix that in a second. We're going to be having a Q&A session with our guests. So a lot of stuff to look forward to. And Thomas, I'll hand it back off.
All right, so broadly, what we've done is basically split up the large QC industry field, and it is large, surprisingly for how new it is, into two sort of categories. There's the quantum software companies and the quantum hardware companies. For the quantum hardware, almost all of them that do hardware also do software. It's pretty rare that there's a company that just does hardware. But we're going to start off by talking about the quantum software before we get there. So the first sort of companies are quantum algorithm development companies. And these are basically companies that they are transferring the classical algorithms that we run on classical computers so that they can run on quantum computers for the purpose of solving some problem or fixing something that classical computers can't quite do very well, like those search algorithms, like that prime factorization. So we have just a list of a few of those here, like the Zapata Computing, QCware, Brocco, D-Wave Systems, as well as Amazon. And they all sort of market themselves in the same kind of middleman. You come to us with a business problem and we'll turn around and give you the quantum algorithm that will fix this business problem. But yeah, they basically, they're in the market of developing algorithms that will solve problems using quantum computers.
All right. So on a kind of similar vein, we've got quantum error mitigation. So as it stands now, our quantum computing is a little bit noisy. So we don't necessarily have perfect coherence, and we get some noise and incorrect calculations when we do it. So with traditional computing, what we might do is redundancy. So that if something fails, we might fall back onto that. Well, in quantum computing or quantum physics period, there's something called the no cloning theorem. So you can't really duplicate the states exactly. So we need to find other ways to be able to correct these error measurements. So that's kind of what these companies are trying to do. They're trying to basically make quantum computing more accurate, and as it becomes more accurate, it's more viable. So you've got companies like Q Control who are basically more on the software end of things, taking the data and trying to reverse the errors. And I guess a lot of them are, and then Quantum Benchmark and Zurich Instruments are also fairly similar as well in that respect.
All right, so this last sort of group of the quantum software companies that we have, we're just listing as quantum software platforms, which is essentially because what they're trying to do is create a like a programming environment for people to run, different sorts of quantum circuits nicely in one place. So it's less about developing actual algorithms or less about actual error mitigation, and more sort of like a VS Code or Eclipse kind of grouping of different quantum tools into one piece of software.
All right, and kind of like mentioned earlier, so with quantum computing, we have a huge potential for a very, very secure method of cryptography. So Ishan actually did a workshop on this. So sorry if I mess anything up. Ishan, please correct me because I see you here. And Matt, I forgot about Matt. Yeah, Matt, both of you guys did it. So actually, Thomas, do you think I should hand it off to one of them because they can probably explain it much better than I?
I mean, if they are willing to speak about it a little bit, that's
if one of you guys actually want to talk about it, then by all means, please. Either, and if not, I can still talk about it.
Is Matt here? I thought he was here.
He was.
Looks like he's not. Okay, I guess I could talk about it briefly. So quantum cryptography is the, I guess, the process of being able to encode and send messages such that it is physically, I guess I should say mathematically impossible for someone to be able to figure out what the message is just by intercepting. So like with a classical way, what you're basically doing is you're sending a key across some kind of secure channel so that both parties know how to encrypt and decrypt messages. And if that key gets intercepted in a classical system, then your communication is no longer secure, obviously. However, with quantum cryptography, you can make it so that it is impossible for the key to be intercepted without both parties knowing that it happened. And so you can then always be sure that your key is not getting intercepted, in theory.
Awesome. Thank you, Ishan. So there's a couple things that go along with that. There's the actual distribution of the keys and the sending of the information. And there's also something that goes along with it, but isn't in a similar vein. So a big part of security is with random numbers. And if you can reverse the way that the random numbers were made, because random numbers as they are now are pseudo-random. They're based off of things like epic seconds in your device or some algorithm on a prime number that's most likely based off of that. So if you can reverse that, then it's not as secure. But with quantum computing, there are algorithms that allow you to create perfectly random numbers. So companies like IDQ and Infiniquant, they are working to basically make that viable and things like this. And yeah, Infiniquant and also Quantum Exchange, they're working on the actual, like what Ishan was talking about with the perfectly secure key distribution. All right, so next these are more companies that are specialized before, but with full stack quantum computing companies, these are the ones who develop both hardware and software. So if you can kind of slide. So these are the ones that a lot of people know, too far. You got like IBM, you got like Google and companies like that. So IBM, to call them out, and because we talk about them a lot as is, They actually developed Qiskit. So Qiskit is what essentially has pretty much become the standard for programming and quantum computing is. For those of you that don't know, it's essentially a Python library that you can use to program quantum computers with. And I believe that is what the hackathon that is this Saturday will be using. So those of you who are going to that, look forward to it. And if you don't know it, hopefully you will by the end of the hackathon. So another one, less popular, but still prevalent, is Google's Circ. So it's another library for quantum programming. And they, the two companies are essentially the big ones that people think about. But you've also got companies like Quix and Xanadu and Intel and a lot of other ones who are also trying to do similar things. IBMQ has partnered with Microsoft. So right now, Microsoft has the Azure cloud platform, which is cloud computing. So they're working to make the Azure Quantum, which is cloud quantum computing, if I'm remembering that right. And yeah, so there's a couple more on there, but that pretty much gives you a good idea about what full stack quantum computing companies do and are.
Yeah, so that was a lot of information, obviously. A lot of companies that we talked about, and there didn't get into too much specifics about any particular one. We'll probably get into more about IBM later once Sebastian, I saw he unmuted there. He expecting him to come in and correct us.
I'm mostly going to talk Microsoft. Is what I was going to say.
Oh, interesting.
Kidding.
So of course, we don't expect you to know or remember all of that. But all of the, I'll just go back one slide to show all of the links to the companies. Come on, computer. At the name of the company, once after the presentation is over, we will release the slides, and the names of the companies are hyperlinked straight to their websites. So if any of those sounded interesting to you, even if it was just the category that we put them in, not even necessarily one specific company, this link will take you right to them so you can learn more about them. But let's get into
learn more about IBM. Stick around for the Q&A and you can ask Sebastian about it.
Yeah. Let's get into the even more interesting and totally not dry part, which is talking about job qualifications. So there's going to be a few slides going through essentially, we looked at companies that we put on the presentation, and we'd go to their website, and if they had a careers tab, we'd go to that and see if they had any sort of job listing currently, and then we just sort of go through what were the qualifications that they were asking for that job. So yeah, so this first one for Rocco, they do pretty much specifically the quantum chemistry simulation, and so they're asking for a PhD in chemistry and machine learning, or machine learning, either or. But whichever one you pick, they want you to have experience in the other one. You need to have a pretty advanced education and experience for that one. The Pascal one is a little lower. Pascal is more about the quantum software. And so, they're sort of asking for the master's in CS or physics, but still, with especially experience in Python. And that's sort of going to be a common theme that we'll see through all of these. AQT also, they do, I think they're full stack. They do hardware and software. And so they're also asking for a master's degree in like CS or something related, with especially a significant background in Python. Q-Control, I believe Q-Control does more hardware, and so they're asking for a PhD in physics with experience in these sort of the quantum circuits and any sort of the physical hardware of the quantum computer. And is there one more? Yes. And then Agnostic and QBraid. So Agnostic is asking for a master's or advanced BS, advanced bachelor's, which I'm not sure what that means. I tried to look it up, and it seems like an advanced degree just means master's, but they would like, sort of like a master's degree and experience in Python and knowledge of like QC algorithms and stuff. And then QBraid, which is more like quantum software again. They're sort of asking for like a bachelor's in physics or CS or something related with a decent amount of software experience, and especially with Python. So what is the summary of all this? If you want to work in QC software, you need a bachelor's degree, and really what you want is a master's degree if you want to be more competitive at these positions. Specifically in computer science is the best, obviously, because it's sort of software, but the more sort of physics knowledge, the more knowledge you have of the hardware and of the actual like algorithms, the better you're going to be as an applicant. Specifically in terms of languages, and this goes for both QC software and QC hardware, Python seems to be the one that if you're going to learn one language really well, that should be the one you learn. And moving from that to hardware, master's degree in physics or something related with PhD likely and probably more what you need to be competitive. Again, knowledge of QC hardware, and if you know some QC software, that's good as well. But also experience with Python. So the bottom line that we found out when we're trying to do the research for this is basically know Python really well, and then know as much as you can about the actual hardware, like the physics behind the hardware, as well as some of the algorithms that the software runs on. And so we're just going to do a little plug that we will be giving a mini course on Python in week 5 of this quarter. The specific date is still up in the air, but since Python is very relevant to these sorts of jobs, and I'm presumably if you're here at this workshop, you're looking into these sorts of jobs. If you have no idea what Python is or how to use it, then this would be a great place for you to start.
All right, so now for the moment you've all been waiting for. So now, Sebastian, he is the global leader of IBM's academic partner program, but I would like to let Sebastian introduce himself because I'm sure there's a lot of stuff that he has to say about himself. So Sebastian, please tell the audience, a little bit more about you.
Sure. Thanks, Andrew. I'm going to share some slides, if that's all right. And I'll give you some context on, it's disabled at the moment. Still disabled. While you're enabling that. So so I joined the IBM Quantum team in 2018.
You should be good now.
Okay, cool. To sort of set up the academic partner program. All of IBM Quantum is really, it is interesting. Sorry, it's showing me yellow triangles with exclamation marks everywhere. Let me see if I can actually do that. Oh, great. More Zoom security. Open system preferences. Never mind. I'll just keep talking. All right. So IBM Quantum is really it's being developed out of IBM Research, right? IBM Research has got a very, very long history in quantum computing, really going back to the origins of the field, which is coincidentally the conference that really kicked off quantum computing was 40 years ago this May. It was held at Endicott House, which is a property that MIT owns, and it was jointly held by MIT and IBM. And Feynman was there, and Toffoli, and a bunch of other super famous people. I
don't want to interrupt you, but
Sure.
I made you host, so maybe.
Yeah, no, it's on my end.
Work,
I'm simultaneously trying to. If I sound distracted, it's because I'm digging through my preferences because this new version of Zoom is not.
Okay, no worries. I wondered if it was just because UCSD was like, no sharing for anybody who's not the host. All right.
Just a heads up, you will probably have to restart Zoom. I've had to do that before.
Delightful. Okay, but I'm not even going to bother. I'll just talk to it. Apologies, but anyway, I'll send the slides afterwards. There's some good stuff in there. So the field's not that old, really. 40 years is not that old if you think about it. It really started in physics. It started really actually looking at the physics of computation. So trying to expand information theory, the field of information theory, to encompass the math of quantum mechanics. And in fact, one of my colleagues at IBM Research was the first person to write the words in quantum information science down on a piece of paper. And it was one of the people who instigated that conference where they kind of convinced Feynman that using quantum mechanics for computation was a good idea. You may have seen the sort of famous quote from Feynman, nature is quantum, and if you're going to simulate nature, you'd better do it on a quantum computer. It's sort of what kicked the whole thing off. You know, since then, obviously, major developments. Really, the hardware that works is a very recent development, right? We couldn't really make more than a few qubits until probably 10 years ago. And at this point, we've got, you know, there's a few different flavors of qubits out there. IBM uses superconducting technology, which is a Josephson junction down at the bottom of a dilution refrigerator, and which is controlled by microwaves. The chip we have now is 65 qubits. So we're actually running 65 qubits for our clients right now. And we just announced a roadmap in the fall where we're supposed to have a beta of 127 qubits this year, 433 qubits the next year, and over 1,000 the year after that. So you can see that the growth is ramping up quite quickly. As you pointed out, they are not perfect qubits. They're what's called noisy intermediate scale quantum devices. It's a term that Preskill at Caltech coined a few years ago. Until we have fault tolerant qubits, we won't really make much progress on the factoring of large numbers to their primes or other computationally precise jobs, right? Because the errors that are introduced make the results pretty useless pretty quickly. But on the other point, the chemistry simulation, other simulation of open quantum systems, there's some real advances that are happening now with the size of machines that we have right now. There's a group, Pri Narang from Harvard, Sabri Kass from Purdue, and David Mazziotti from UChicago, and Katie Head Marston at Harvard as well. They're doing some really interesting work in simulating open quantum systems and sort of developing generic approaches to doing that. So things like chemical reactions, material science. David Mazziotti actually used the 53 qubit machine last winter to simulate exciton condensates. So I'm not a material scientist, so something about the way that electrons group on the surface of materials and Bose-Einstein condensates. And he actually said that using the qubits, programming them with gates and with microwave pulses, he was able to make them literally behave like exciton condensates. So he was able to observe behavior in the qubits that is not, I mean, it was a simulation you wouldn't have been able to do in any other kind of lab setting. So even now, when they are crappy computation devices, they are really interesting lab instruments for physical sciences. On to sort of the career view of it. A lot of the information, by the way, that was a really good overview of the way the industry is sort of structured and a bunch of the players in the industry. The first thing that I like to say when we're looking at quantum computing and how to approach it, right, is there's right off the bat, there's a grouping of people who want to contribute to the field of quantum computing and people who are going to want to use quantum computing to do other stuff. And right now, you can't really use it for very much at all other than those simulations of physical sciences, which is an emerging field. If you're interested in the use and you are in chemistry or physics or material science or other potentially pharma or biology, there's emerging applications in biology as well, then that, you can come at it from that direction. You come at it with an advanced degree, which I think you're right, means a master's or a PhD in one of those fields, along with a strong computational background, and start to work on things in that way. If you're looking to contribute to the field itself, then that's further subdivided into roughly hardware and software, and the space in between hardware and software. On the hardware side, you're talking about physics and engineering, electrical engineering in particular, photonics, microwave control, RF sciences, that sort of thing, and even within that, I would say there's also a further subdivision. When you're talking about physics, there's the theorists, and then there's the experimentalists to a certain degree. And they're kind of converging more than they have historically in physics. Historically, there was more of a division between theory and experiment. Now that we have these devices where you can have a theory and then go and implement it on a device, there's a much closer knit kind of relationship emerging between theory and experiment, which I think is really interesting for the field. So physics and engineering on the hardware side, and then looking at, sort of moving up the stack, there's a whole bunch of engineering disciplines in the control stack. So these are devices that are used within the dilution refrigerator. And here I'm just talking about IBM's superconducting technology. Of course, trapped ion is a similar but somewhat distinct set of technologies. Then there's more emerging stuff in photonics and diamond vacancies and other exotic approaches to making qubits. But in the superconducting regime, the dilution refrigerator and all the equipment that goes in it to modulate the microwave control signals, filter them, amplify them, clean them up basically, and then read the signals that are coming back out. There's a whole world of disciplines within that as well. So it's incredibly cross-disciplinary field, and it's not, it's not really proper to say there is a field of quantum computing yet. It's kind of a bunch of different fields that are all converging and coming together. And then, of course, above the control stack, you're looking at various layers of software, from very, very low-level software, which is, in the IBM case, it's called QASM, or Quantum Assembly Language, which is very low-level commands for constructing gates, which are built up out of microwave pulses. So the gates are translated into pulses and transmitted down to the qubits. And then above that, you've got Qiskit, right? So Qiskit actually compiles to QASM, and then QASM is executed on the quantum machine. So there are roles contributing to the control software QASM. There's roles contributing to the things like the transpiler within Qiskit is enormously complex, and will only get more complex. It's doing things like trying to optimize a circuit that someone describes as a series of gates, right, that performs a particular task on the quantum computer. You can do that in Python. You can do that with the Visual Composer. But once you have that circuit, the transpiler takes it and starts applying specific knowledge about the systems that it's going to run on. Like, you need a specific topology because these two qubits have to be beside each other so they can be entangled. This one could be somewhere else. You actually have to map it to physical qubits and optimize, and then optimize for the noise characteristics of that hardware. So there's that's a whole specialty in and of itself in many ways. In fact, to the point where companies like Q Control and CQC, Cambridge Quantum Computing, and a few others are even focusing, just like their startup offerings are primarily focused in that tiny stack, that tiny part of the stack of transpiling and error correction or error mitigation at this point. And then climbing up the stack, of course, you get into Qiskit itself, or sort of the interfaces that people are working with directly. It's an open source project, so if you're looking to get involved, you can actually start, go onto the GitHub repo and start looking at for, there's one site, there's one page that's basically a list of problems that you can start going looking for, right? So bug fixing and easy, relatively easy places to get started. And it's a pretty vibrant community too. So there's a Slack instance that the community runs. So they're pretty, there's actually, it's really gratifying to see. It's actually, as you said, it's sort of becoming in a way a de facto standard. And so there's a lot more than just IBMers who are involved in the building out and maintenance of Qiskit. And it's also being adapted to other backends. So there's an AQT trapped ion backend. There's a Honeywell backend, and a few others. So CQC as well. So there's lots of opportunities for even, there's a biology student at UC Davis who, with a few other students, got together and I sponsored them with some pizza money, basically, so they could spend some time integrating BioPython into Qiskit. So they built an integration so they could, do the modeling of molecules in BioPython and then have that translate into circuits in Qiskit at at least it's a toy problem level at this point, like everything is in quantum computing, but it's a very interesting start on something that could turn into something really great. And then the other, Qiskit is still at the level of describing quantum computing in terms of circuits and gates, which is, if you think about, obviously, if you think of the analogy in classical computing, we're so far further up the abstraction stack, right? We've got high level languages, and who thinks about memory registers and logical gates at this point, right? I mean, I'm sure you take classes where you dig into the theory if you're doing a CS degree, but that's not how we interface with and utilize computers. So the direction that we're going in fact, after the hardware roadmap came out, and I had another nice graphic to show this as well, but you'll have to imagine it and look at it later. After we announced the hardware roadmap, we announced the software roadmap that describes the next few years of climbing up that stack of abstraction. So the next big sort of development will be the release of what we call runtimes, which are predefined implementations of specific algorithms, things like a QAOA or VQE or a state vector machine in a machine learning context. Some of them are combinations of classical and quantum circuits, so that there's like a loop through classical to take the results out of the quantum circuit, do some optimization or select the best result, and then feed the results back into quantum. So they can be these sort of, literally runtimes is what they're called. So they are runtime elements of code. That's going to be a whole other category of software development, writing these runtimes. And then, at the highest level, utilizing these runtimes in more familiar kind of application development settings, right? So the analogy I always make is, data science, machine learning. A few years ago, it was esoteric, and you had to be a stats and math PhD to hand code your own, DeepMind, AlphaGo kind of stuff. And then as it progressed, those toolkits like TensorFlow or an iOS machine learning library or whatever become available and are able to be utilized by developers with a reasonable level of skill and a little bit of upskilling, cross-training on different topics, and then applying it in creative ways to problems that the authors of AutoML or any of these libraries wouldn't necessarily have thought of, right? That's sort of the way innovation works in technology, is you sort of make a tool, create interfaces for other people to use it, and then they go use it for things that you never imagined they would. So that's kind of the end-to-end landscape. In terms of careers, I think that, it being such an early stage, and you can ask anybody how long it's going to be until they're actually good for something, and you'll get a bunch of hand waving. Nobody really knows, right? I mean, it could be a relatively short period of time, or it could be that there are really, really tough problems for scale, for coherence, for quality of qubits, for control of qubits that really just take us longer than we'd hope. So, if you're interested in contributing to the field, any of those companies you listed out, of course, there's in fact growing interest in the private sector and growing competition for the skills. Frankly, I mean, there aren't that many people who have this set of skills that can be applied to the field at this point. So the skills are scarce. There's also enormous opportunity in academia itself. The Biden administration just announced they're going to start ramping up the public investment in R&D and basic R&D. And I just read something today that The NSF apparently in the Jobs Act bill, the NSF's funding is going to be increased by $100 billion a year, which their current funding is $8.5 billion. So significant upgrade. And even the early stages of the National Quantum Initiative, which was signed into law a couple of years ago, which was the vehicle to start the taps flowing for public funding through the DOE and the NSF, that so far has turned into, I think it's the establishment of 8 different quantum centers, which are usually around national labs, so Brookhaven, Argonne, Fermi, and then a collection of universities that are that sort of define the topics they're going to work on. For example, at University of Illinois, UC, Urbana-Champaign, they're focusing on telecommunications. So they're focusing on quantum communications technologies. At Brookhaven, with Yale and MIT and Princeton, they're focusing on qubit design. So looking at alternative qubit designs in the superconducting category, but different ways to design them so that they can get a better handle on quality and error correction. So each of these have a different set of themes. Across those 8 centers, they're going to be hiring 500 postdocs. These are sort of PhD graduates who are going to work in labs with principal investigators paid by government funds to do all kinds of really cool stuff. The amazing thing about those kinds of settings is that there aren't many, in terms of like, if you're curious, if you have sort of broad interests, you can't beat academia and national labs for the exposure to the sheer number of different topics that are being explored, different backgrounds, different skill sets, and really, really deep expertise that's being brought to bear to fascinating science problems. And that, the reason I spend this much time on it is because quantum computing really is a science problem at this point. It isn't a computer technology yet, right? It's a really promising, soon to be, hopefully, computer technology. But if you're looking for the earliest entry points, a lot of those are going to be through academia. So, those 500 postdocs are the result of something like, I think it's a total of like $125 million or $150 million in funding, which is, that was per center. So it's like 700 million in funding. That's just a drop in the bucket compared to where they're going with the direction in terms of public funding. Now, the other thing is that if you end up in going down that path, most of the startups you had on your slide are founded by postdocs, right? They're people who came out of these labs who learned a bunch of stuff from the researchers, from the PIs, from the professors, from their peers, and then they go found a company, right? So it's a very it's a very tight-knit community, and there's a ton of collaborative learning and exploration going on. And the other thing I'll say is that there's right now, I think that the reason you saw PhD all over the place there is because there aren't a whole lot of master's level programs that are specific to quantum computing yet, or quantum information theory or quantum engineering. UCLA is planning to spin up a master's program, I think in 2023, that's going to be specifically quantum engineering. And I expect a bunch more to be popping up. So it won't be quite as daunting. It won't be like PhD or get the heck out of here. It'll be more like, there's ways to get involved at the undergraduate level. There's certainly internship opportunities, plenty of them, and an increasing number of them. And I think there'll be more opportunities and more pathways that get you those master's level degrees where you can start to contribute more. So yeah, I mean, it's an evolving field. It changes rapidly. And I think in part, what's fascinating about it is that, it's coming out of these established fields like physics primarily, but also information theory, computer science, sort of more on the theoretical side, that haven't, like I said, they've been talking about this stuff for 30, 40 years. And all of a sudden you're seeing, not 2 qubits, not 5 qubits, not 4 qubits, but 65, 127, 433. Like those are the kind of curves that we love to see in information technology, because it's like, okay, here's the elbow. We know where this is going, right? So it's super fun too.
So Sebastian, I kind of have a question for you, and it builds off of what you had just mentioned. So from an IBM perspective, because I'm sure all of us here, except for maybe I don't know about everyone here, but most people here are undergraduate. So from an IBM perspective, what qualities would you be looking for in someone for those IBM internship opportunities?
Internships, yeah. It's really a matter of, we're looking for a bunch of non-traditional profiles. I mean, that's part of what we're doing purposefully, because it is such a physics heavy kind of environment. So bringing a general sense of curiosity and a demonstrated ability to sort of, we're going to tend to favor students who are, you don't necessarily have to be already, knee deep in Qiskit or whatever. It's just self-learners, endlessly curious, right? And some kind of I would say a scientific mindset helps, right? In some cases, depending on the school, but computer science can be very sort of software development or software engineering focused. I think that having a little bit more science background can help. And it doesn't matter whether that's, physics or chemistry or biology, but it's just to have a little bit broader than just CS, if you know what I mean. I think that helps a lot. And, I will say that the other thing is just, it's tackling that sort of poorly defined problem, right? It's like the problem is somewhat amorphous, and you're going to have to learn a bunch of skills to even get to the point where you can start to define, what it is you're going to need to do to try to come up with an answer for the problem. I know it's vague, but that's that's kind of, I will say also there's a lot of competition. The demand for the internship positions has gone through the roof as well. So we're doing a lot to try to get we bring about 100 people in right now each summer for quantum internships, and we're trying to encourage other industry players to ramp up their efforts as well. And there's another NSF program called Q to Work. I think they're going to be launching a website soon this summer, I think, which will be sort of a collection place for all of the opportunities that various companies and government entities are spinning up and sponsoring. So hopefully we'll get a bigger collection, because at the moment it's I think there's not enough to go around for the demand right now, which is a good problem to have for us and not so much for you. I went through a ton very quickly. Anything I went over too quickly, or anything you wanted me to dig into more?
That is a good point as well. If anybody has anything they want Sebastian to maybe go over again, or us in our presentation, feel free to put that in the chat and we'll get to it. I had a question as well. Obviously, like this is, it is a science problem, like you said, and you need to have a college degree to get into these sorts of positions. I mean, even the internship, realistically, you need to be an undergrad. But what is some of a skill that you see as being very important that maybe isn't necessarily taught in schools, or isn't one that you would just get by having a degree?
Yeah, it's a great question. I actually just interviewed Charlie Bennett, that pioneer that I just mentioned, who's still at IBM, and was the first person to write quantum information theory down. Also, by the way, he read a paper by a colleague written in, I think, 1968, that was talking about using quantum mechanics to make money that would not be counterfeitable. And he realized that could be applied to protected communication, and did with another IBM colleague, I mean, wrote a bunch of papers on quantum, encrypted communication, and has, basically is one of the pioneers of that entire field. So anyway, Charlie started in biology, and I think he said that he was at Harvard. They had science. Sorry, there was a computer science seminars, and he went to one and got interested in information theory because he noticed right away that the way that RNA and DNA encode information has some striking resemblances to the way information theory is described. And Turing machines with the tape, encoding information, reading information with the tape head is a lot like transcriptase and RNA. And so he sort of jumped over into information theory, when I asked him, like, what advice do you have for people getting into the field? And he said, broad curiosity. So like making connections with things that you wouldn't necessarily think there is a connection with, right? And then the other thing was patience. He said, science isn't something you can sort of predict the pace of progress on. It's the process is coming up with theories and then disproving them, right? Like you don't really know how many times you're going to have to experiment with something to eliminate all the things it isn't. I mean, Edison famously tried, I think, 100,000 different materials for the filament for the light bulb before he hit on something that worked. It seems like he'd start with tungsten right away, but hindsight. But anyway. So yeah, I mean, I think that, it's a really, like, I love information technology. I love the history of information technology. I'm old enough that I remember the early days of the internet sort of becoming commercialized, right? Coming out of the universities, coming out of the government funded research, and starting to be something that people used for applications that nobody expected, right? I mean, news groups, social media, like all of that stuff comes out of these early experiments and trial and error around networked application protocols. It took a lot longer than anybody thought in some ways, and now it's ubiquitous and embedded in our society in ways and doing, and things are changing things in ways that we could never have predicted. We're at the very earliest stage of another wave of technology that will be that transformative, right? I mean, that's as long as we can make these things. There are always skeptics who's in any audience who are close observers of quantum computing who say, like, we'll never get there and never get enough qubits, they'll never get error corrected. But every year the machines improve at a rate that seems to imply that we are going to get there. And if we get there, I mean, the stuff that people are talking about being able to simulate are like photosynthesis, right? Like that would be pretty cool to be able to figure out. The nitrogen fixation, right? There's I can't remember the name of the chemical reaction, but we use a chemical reaction to create synthetic fertilizer for the world, right? And it uses an enormous percentage of the energy that we produce in the world, and an enormous amount of pollution comes out of it. Well, there are bacteria that fix nitrogen in scummy pond puddles using almost no energy at all, and having certainly very little. I think the waste is like water and, I don't know, acid or something, but something is easily dealt with, right? That's another thing. It's chemistry, which is a quantum process. So if you can simulate it, you might be able to replicate it. And if we could make, we could synthesize fertilizer with no pollutants and no energy consumption, that'd be pretty cool too, right? I mean, the thing is, just in the sphere of natural sciences and physical sciences, the things that it can be applied to are, completely earth-shaking, right? They're disruptive on a level that things, you'd have to look at like the printing press or internal combustion to find things that are similarly disruptive. That's super exciting to me. And those are just the things that we're anticipating it could be used for. The unanticipated are the ones that are really going to be exciting, right? Because until you make, I mean, someone told me just the other day, or actually around the time we announced the roadmap, and we were saying 1,000 qubits in 3 years, they were saying, like, if we had 1,000 qubits today, even like if we had 1,000 error corrected qubits today, we wouldn't know what to do with them, right? Because there's this incremental iterative process going on where you make a few more qubits that are usable, and then they try to figure out what you could do with a few more qubits. And every stage of the way of this progress, they learn a little bit more. They figure out something that they did not know at a smaller stage of these machines. The software gets a little bit more sophisticated. New ideas come into play. So this is a very long answer to your question. The answer is, as curious as possible, bring stuff in that people aren't thinking about, because that's where breakthroughs come from, right? And the earlier the stage of the technology, the more there will be unexpected emergent applications and breakthroughs.
So you'd say it's just as important that we have people who are thinking about like what to do with them. So you don't necessarily have to know everything about quantum computing. You just have to have some idea about what can we use it for.
Yeah, I mean, you know, it's not. It's most likely the sort of the productive incarnation of quantum computers. When we have quantum computers that actually can do useful work, it's going to look a lot like GPUs, right? It's going to look a lot like I've got an application that does this broad, let's say, business process, or it's a consumer application, whatever it is. And there's this one thing that's computationally very complex, and I'm going to grab a library and I'm going to embed it into my application, and I'm going to use a quantum computer to accelerate that one stage of my computation, right? And that's in the foreseeable future, that's going to be the way that they are implemented almost universally. So, like, if you're not interested in becoming, you know, sort of trying to contribute to the field and the core technology of it, I do still recommend, like, familiarize yourself with Qiskit and with the other software packages that are out there a little bit, just to do their hello worlds and poke around a little bit, so that you get a sense of what it is, so you can keep an eye on it, right? Because at some point, if you take a career path that is not directly in quantum computing, there will be a point in time where it starts to be useful for all kinds of different types of applications and different industries and different business problems. And you want to be familiar enough that you go like, aha, I remember how to do that, and go back to the IBM site, hopefully, or somebody else's, and grab the tools and start implementing stuff, right?
I did sort of just want to agree with what you're saying. It is interesting that because quantum computers are so, I don't want to call them not useful, but not particularly useful as of now. And yet it requires so many years of education and training in order to sort of work on them. It does create this interesting situation where people that don't have any of that training at all might have just as many ideas of how to use them, because the uses for them right now are so kind of trivial and not that important. And so everybody can have some genius ideas, regardless kind of how technically expert you are on the actual physical quantum computer.
Yeah, that's right.
Which I guess is just sort of like a yes, it is daunting how many years of education it can be, but we can all have great ideas, regardless of the fact that, you know, all of us here, excepting you, are far and away from any sort of heavy sort of quantum job.
And also, by the way, like, again, if you're not contributing to the core of the hardware or the software, whatever, there's all kinds of jobs that are being driven around this, right? I'm not particularly technical, I used to write software a long time ago, but I got into the business side, and I'm setting up partnerships and programs and managing the research, the collaborative research we do with external parties, and talking to groups like this. So there are also software developers who build our website, right? Who build the Composer, which is a web application that visualizes the circuits. They know a little bit of quantum computing because they have to understand, basically what the gates do and how they should behave and stuff. But it's just plugging into the Qiskit backend, right? They're not Qiskit developers. They're writing the visual programming environment. So, there are, if you want to be involved in quantum computing, there is a way, guaranteed. Many ways.
Yeah.
One of the slides that is in the deck that I will send afterwards is it's a single slide. It's kind of an eye chart because they're small printing, but there's something like 140 different types of jobs on that slide that are all related to quantum computing. They're just like what we could come up with.
Right.
That'd have been nice to have.
Yeah, well, I'll send it later.
So it doesn't look like we got any questions in the chat regarding anything we said. Again, if anybody does have any sort of questions, feel free to put it in there. I have one more question that I would like to ask, and if after that, okay. Audria wants to know, when is or was the internship due?
Yeah,
the most important question.
Yeah.
Why you're here.
We open up internships in September for the next summer. So by, I think, November or so, all the summer internships are filled. So they're all filled for this year. But they'll open again in September. And in the slides, you'll see that there's links to the internship things. We're also, as I said, we're trying to help the industry scale up. So there is a program that we launched with Princeton a couple years ago. We skipped the COVID year, but we're doing it for the second time this coming summer. That's also full already. But the reason I mention is that there are more and more. So we do it. So it's the first half of the internship is at Princeton. The second half is at IBM. So, and that's the sort of model we're trying to encourage, so we can try to get more bandwidth, because because there's a lot of demand, and we frankly need to be ramping up our training and recruiting activities, because we need more people in this field.
Right. So I had one more question I wanted to ask you, and this is obviously different a little bit because of COVID. But I was curious to know what sort of like a typical day, and I guess this also depends on what exact job you're doing, but what is a typical day in the QC industry like?
Yeah, it depends a lot on your role, because like my friend Pat, who manages the lab in Yorktown, where the prototype machines are stood up. Right now, he's managing a whole team of engineers building the world's largest dilution refrigerator, the super fridge, as they call it, which is, I mean, most of these dill fridges are, I would say, they're probably like, it's a cylinder. I think it's like 5 feet tall, maybe 6 feet tall, suspended from an aluminum rack, and a diameter of about 2 feet, maybe 30 inches. This thing is big enough that 2 people can stand inside it. And he's making it that big because that's the scale that we need for 1,000 qubits. So he's working on the fridge that's going to house the 1,000 qubit machine. And he's a physicist, but he would tell you he's more of a mechanic. Like he's got a monkey wrench in his back pocket, and he's got scraped up knuckles every time I see him. So he's building physical systems. He's bolting stuff together. He's wiring things up, and his whole team are doing that. And there's a whole bunch of people at Yorktown who are doing that. There's also chip fabrication, right? And then they take the chip out of the fab that happens upstairs, and they go into the characterization lab, and then they're wiring it up and putting it into a dill fridge and testing it out and collecting data and results. Software development is software development. I mean, probably in somebody's basement somewhere, right?
Yeah.
We all develop software from wherever we are, basically. And then there's a lot of on the business side, the community side, this sort of growing the ecosystem, as it were, of people who are using and affiliated with our stuff. There's in normal times, a lot of travel, a lot of going to conferences, a lot of meetings in various cities and stuff. Even actually, I would say especially on the algorithm side, the people who are working on algorithms and applications for quantum, they tend to have a lot of conferences because there's a lot of long distance collaboration that goes on, but because it's so demanding, it's so analytical and abstract, it's in-person communication tends to work better for that kind of academic paper and academic collaboration. So they do get together a lot. So like the APS, the American Physics Society, has a meeting in March that's huge. That's sort of the big event. But then there's quantum information processing as an annual there's tons of annual conferences. And then of course, that's kind of intersecting now with the tech industry. So there's conferences like around HPC and supercomputing. They're now starting to have quantum elements in them. And so there's cross-pollination going on. So I don't know if that really answers your question, but it depends a lot on your role. But I think mostly if you're dealing with the physical machines, you're in the labs and you're doing, bolting stuff together and wiring stuff up. And otherwise it's software development or academic research.
Yeah. I mean, it was not an easy question to answer, I guess. It was sort of, what is the meaning of the universe? What is give me all the
That's
information
easy.
that you have. Yeah, so I don't know, Andy,
Exactly.
do you have any other questions that you wanted to ask?
Kind of. So going back to that internship thing, what would you say specifically that the interns would most likely be doing? Because they're not going to be doing high-level research,
Right.
nor are they going to be doing hardware development.
Right.
I feel like I'm interested to see what they do.
Yeah. So typically we spend probably the first half on training, right? So it's essentially, I mean, in fact, last year, because of COVID, they basically developed 2 weeks worth of training and delivered it all remotely to about, last year we had about 75 interns after a few people had to drop out for various reasons because of the pandemic, but everybody else was remote. So we ended up with 75 and they delivered the training to the 75 interns and then realized there's no reason why we shouldn't do this for everybody. So they then did the first quantum summer school last year, which was the same material and ended up having, I think, 4,300 people go through it. So even if you don't get into the internship, I mean, it's too late to get into the internships this year, but the summer school will be happening and there'll be links to that as well in the slides. And yeah, I mean, that'll get you at least the experience of the first few weeks of being an intern without actually being there. But then from then on, it's mentorship and it's in most part, you're right. I mean, it's a lot of it has to do with getting more familiar with Qiskit or getting more familiar with how the lab works, depending on where your interests lie, right? I mean, there are definitely interns who work in the labs who help put help set up the DIL fridges or run the characterization experiments, that kind of stuff. And then there's on the Qiskit side, there's anything from working on the Qiskit internal, so like hunting down bugs and adding features, or helping try to test and develop the algorithms and the applications side of things. So I mean, we get pretty good reviews. Actually, I think it was something like, well, everybody said they would recommend to any of their peers to do it. I can't remember what the N was, but it was fairly large.
So I guess this might be a bit of a sacrilegious question, but do you know what they just, I mean, because this is a generalized a workshop, do you know what they might do at other companies? So if someone got in as an intern into, say, Intel, what do you have any idea what that might look like?
It's a good question. I don't really, but I imagine it would be very similar. Although, I mean, Intel's a sort of a special case because they, so far, their involvement in quantum computing is they released, what was it called? Something bridge, horse bridge, maybe? No. Anyway, they released a control chip that's used in the cryostat, inside the dill fridge, in the cryogenic environment, but it isn't. It's not a quantum computing chip per se. They are still developing one, but they haven't really talked a whole lot about it. So at this stage, I don't know what it would be like, but I imagine Intel also would be much more heavily on the hardware side. I don't think they are doing a whole lot. I mean, certainly, if they are, it's in stealth, right? Maybe they're developing a whole SDK for their qubits as well, but I suspect not, because that's not where their core competency is. But I mean, in any intern program, it's a mix. There's a certain amount of training and there's a certain amount of hands-on experience, right? So you're going to get some amount of instruction, and it'll feel a little summer schooly, but there'll also be projects that get you sort of hands-on experience, whether that's hands-on keyboard or hands-on a wrench, depends on sort of where your specialization lies.
Actually, I wanted to ask a couple questions as well.
Sure.
So the first one I wanted to ask was, you talked something a little bit about kind of getting higher up the stack with quantum programming. So I wanted to ask you about that, and maybe introduce the example of like machine learning, where if you 15 years ago, if you wanted to do machine learning research, or if you wanted to build a machine learning application, you had to actually program the thing yourself, right? And go through all the steps and do all the math, right? But now they have all these libraries that exist, and you can kind of plug it in, and or use something that's already been written, change it up a little bit, and then run it on your own thing, right? So my question is, do you foresee that kind of existing for quantum computers? So, like, for example, like a quantum Fourier transform.
Yeah.
Maybe that could be automated, and then you could kind of use these bits and pieces, the same way maybe like gate level processes on a classical computer are automated up to the assembler, and then to a higher level language like Python or C++ or something. I want to ask you about that. Maybe what you think might be the timeline for that. In the next few years.
Well, I mean, like architecturally, we're starting to do that right now, right? Like, so we just announced Qiskit is sort of evolving, and there's now, they're calling them application modules, but they're essentially that runtime concept that I described before. So, and I believe the state vector machine is one of the first modules. So that's in the machine learning space, right? And it's a pre-built state vector machine implemented with quantum circuits. So you don't have to go to all the trouble of hand coding the gates, and you just provide it with your inputs and then get the output out of it and go on your merry way. So that's happening right now. In terms of when it'll be useful, again, that's the evolution of the hardware platform. So it's sort of could be a couple of years, could be a lot more years. But yeah, I think that, like I said, I think that GPUs are a pretty good analogy in many ways, other than the fact that you won't be slotting them into the back of your home-built PC. They will be up in the cloud, because nobody can afford. The little dilution refrigerators, by the way, super cool. They literally they are cool using a combination of two different isotopes of helium, and I can't remember which one is I think helium-4 is the very common one. Helium-3 is the not common. It could be the other way around. Anyway, the rare isotope of helium, the little canister that you've got to pour into the dilution refrigerator is $50,000 every time you fill one. So that's why you'll never have it in a card in the back of your PC. But
it's almost as expensive as printer ink.
Yeah, HP should get into that business. But yeah, so the analogy though with machine learning and data science is an apt one, because GPUs are used, as the workhorse at the bottom of the stack, and then there's layers of abstraction that make it easy for an application developer to implement machine learning in their iOS app or whatever, right? And I foresee that being the same pattern. I could be wrong, but that's what all signs point towards. That's the way it's going to evolve, because as I said, there's a group of people who are trying to contribute to the field, to the hardware, to the software, to the algorithms, but the natural output of that is going to be higher level abstractions that a more general developer community is able to use.
Huh. That's interesting. And then I guess the second thing I want to ask is a little bit more, I guess maybe self-centered or so for me, because I have a couple questions about like degree paths and stuff, but it'll be useful to other people as well. So I'd like to ask you about, so I'm, as most of the rest of us, I'm an undergrad, and I'm kind of trying to think about what I want to do after I graduate in about a year or two. So a lot of these, like this high level research, right, kind of requires a PhD, and that's something I'm considering, possibly getting a PhD. Although it is a lot of time. I'm already 24. I'm not sure if I'm looking to spend that much time, but that's something I'm really interested in. If I might possibly get a really good deal or a scholarship or something, I might pursue that. But the question I wanted to ask, I guess, is so if you actually want to design these things, right, and try and build these systems, and you're not just working on some really specific thing like building a dilution refrigerator or whatever, I would guess that's probably PhD level, right? Being really involved in that.
Building a fridge would be more EE or ME, right? Those are more engineering kind of tasks. You're thinking more specifically in CS?
Well, actually, so my major is engineering physics.
Okay, cool. So, as I said, UCLA is spinning up an engineering master's degree in quantum engineering is what they're going to call it. So that's something to check out, and I can connect you with some of the folks who are involved in that if you're interested. I think that it has historically been dominated by PhDs. I think that's one of the things that we're going to see change over the next few years, because frankly, the field is expanding too quickly. There isn't that big a supply of PhDs. The pipeline is not magically going to expand by 100-fold, right? And that's probably how many, what the expansion of the workforce looks like. So like other fields, right? I mean, as I said, again, going back to data science, data scientists were PhDs in math generally when in the emergence of that term, right? When we started to talk about data science, maybe 10 years ago or 15 years ago or whatever. And it seemed super esoteric, and it seemed impossible to use in a more general developer kind of context. But that has democratized, right? I mean, there was a gradual evolution of the field to now it's not as easy as being a DBA, but it's not as hard as being a PhD either, right? It's somewhere in the middle. It's much more accessible. So, we're at the earliest stages of that. So I think that it's still heavily weighted towards PhDs. But, what's going to happen is that we're going to see increasing pressure on the labor market in this field because of public funding. I mean, going from whatever, I think we're currently, it's 0.6% of GDP goes into R&D. And Biden's saying he's going to increase that back to 2%, which we haven't seen that kind of spending since the Cold War, basically. So that's it. And he's called out quantum computing several times specifically. So a lot of that is going to go into quantum computing. So that's going to increase demand enormously. It's also going to increase the incentives to universities to create more and more creative programs, because there's going to be, and then of course, because the public spending expands, the private investment is going to go up as well, because the industry knows from experience, the government invests in advanced research, it turns into the internet turns into a huge commercial opportunity, right? So we're not going to sit around as a private sector industry and not chase the government spending with companies and startups and offerings that are going to capitalize on the output of all that research. That's why we invest in research as a country, right? There's a natural growth factor that happens from that. So all of that is going to create enormous demand for these skills. So I think that's going to force creative thinking about how do we apply people who don't have a PhD to doing useful stuff in this field. And it'll force the development of that abstraction up to higher levels in terms of software. It'll force the creation of smart sort of cross-training or apprenticeship-based programs where you can take somebody who's at a master's level or who's advanced. Maybe they're in mid-career, but they're in non-quantum RF for engineering or whatever, and cross-train them into a quantum context, right? I mean, it's going to demand a lot of effort to fill the demand for this field.
Interesting. Yeah, because I guess my worry was if I got a master's, in I guess probably electrical engineering, or maybe physics. I'm personally more interested, I guess, in the hardware side. So, a lot of it, like the superconducting transmons and all this stuff is really interesting to me.
It's pretty cool.
For sure. So yeah, let's say I get a master's in electrical engineering or physics or maybe UCLA's program or something like that, right? Would I be doing I guess you kind of answered that a little bit in that they're trying to bring in more people with less super high level PhD expertise, right? But would PhDs still be really designing all this stuff and making all these higher level decisions?
I mean, it's not, none of this is going to happen overnight. So the immediate answer is yes. The longer term answer is probably no. I mean, as an example, one of my colleagues, Latko Minev, just released, and a team released another open source extension of the Qiskit software, which is called Qiskit Metal, which is a GUI for designing superconducting qubits. So it's the beginning of software-aided design of these qubits. And obviously, I mean, that obviously opens the door to writing software to simulate how those qubits will perform, right? Once we have more knowledge about the variations of characteristics that emerge out of certain design techniques in qubits, we can surface that into Qiskit Metal, and you can lay out a qubit design and then simulate what the noise is going to look like to decide whether or not it's worth building, right? So those kinds of tools, they're ways of capturing super esoteric, super specialized knowledge in a software package that you have to have a fairly high level of skill to be able to use, but not as high as the person who wrote the thing, right? I mean, that's the beauty of software, is like when you capture knowledge and know-how in a software package, you've allowed somebody to use that without actually going through all the pain to attain all of that knowledge and know-how that you needed to actually write the software package. It's cool. So yeah, I think that what I'm talking about is a gradual process, but the thing I will say is, if you're looking at the IT industry right now, technology industry generally, barring actually even there is no way that investing in a career path that is going in the direction of quantum computing is not going to, basically, if you like it, you're set up for life, because it's like it's 1992 and your favorite thing is the internet that Stanford and MIT have between them. Like pretty good entry point for a career. Like, it's now whatever 30 years later, and the internet rules the entire world. So if you were involved that early, you probably are doing just fine.
Yeah, you look at us, we're talking on the internet.
That's right. That's right. Yeah. So I mean, it's not entirely. There's lots of potential bumps and on the road. Like it may be that there are limits to what we can do with these devices from a computational perspective, but they're already proving that they're valuable from a simulation perspective. They're already proving that they're incredibly valuable from a sensing perspective, right? There's early work going on in using quantum devices for the equivalent of MRI machines or GPS or radar that are like extraordinarily sensitive. Even if we don't end up with a universal quantum computer, fault-tolerant quantum computer, imagine the skills and the knowledge it'll take to know what to do with the data that comes out of a quantum GPS, for example, right? I mean, that's still specialized knowledge. It's still familiarity with the field is going to give you a leg up for building the software and the applications that use these quantum devices. I mean, who was it? Oh, it was Misha Lukin at Harvard said to me just in a meeting I was in with him a few weeks ago, we're entering the quantum age, and what he meant by that is that our engineering skills are now at the level where we can create devices that are active, that work at the quantum level, right? Which is kind of astounding. I mean, Junyi, who is the main researcher at GILA, where the atomic clock is, where the most accurate atomic clock is housed. I saw a talk by him. He was saying that his atomic clock is so sensitive that it is in effect a GPS, because if it's a foot off the ground and then you raise it to 6 feet off the ground, it can tell you to within a few millimeters how far off the ground you've moved it, because it's further away from the gravitational center of the Earth and the time has changed. Like the duration of each tick has changed enough for it to tell it like, oh, you just moved me 6 feet up. Like that's a level of sensitivity that again, like I said, we don't know what we're going to do with these things. We're just at the very, very, very beginning of starting to make these devices and explore what they might be good for.
So, kind of to piggyback on that, would you say that by the time a lot of the first years, second years, and I guess now is going to be incomings, graduate, there will be more opportunities open for people with those lower level degrees compared to now?
Yeah, I think so. I mean, there's two things, right? As I said, there's two factors. One is climbing up the abstraction stack, so diminishing the barrier to entry for getting involved in these things, right? And the other is just the stress of the labor market for this field is going to require creative approaches to cross training, up training, whatever, taking people from outside of the normal pool and making them productive and useful in this context, because the demand is going to outstrip the supply very, very quickly. I mean, like I said, the level of investment is going from, I mean, let's just say the NSF invests the same amount in all the different areas of sciences that they cover, right? They don't, but whatever. So they've gone from roughly 10 billion to 100 billion. So they have 10x the money to spread around just in quantum. If it's equally distributed, it'll probably be more quantum, frankly, than other topics, because that's kind of the mandate, right? So that's 10 times the number of recipients of NSF awards for doing research. So where are these people, right? Like that's just at the NSF funded level, right? There's, I mean, for example, IonQ just did a SPAC, right? They did a special purpose acquisition company. They essentially went public sort of backwards. They got acquired by a public company that doesn't do anything. It's sort of a shell company. But it's a way of doing an IPO now without really having a mature business. And it's quite popular. Anyway, they were the first quantum computing company to do a SPAC. They raised $650 million in cash from doing that, which they are going to burn on hiring people. And they're just one of the many companies out there with increasing amounts of investment and increasing efforts in this field. So there's no indication that this is going to slow down at any point.
So Ben got to kind of ask a little bit of a personal question, so I'll do
Go
the
for
same. So I personally, when doing my research before college, saw that the two big majors that people want were physics and computer science. And rather than picking one of the two, I split the difference and took both. Do you think that I should say, obviously it's good to have both, but would you say that it's a particular advantage, or is it more of a, I guess, a bit of a luxury?
No, I think that's an advantage for sure. I mean, I mentioned sort of the traditional split between theorists and experimentalists, right? Before we had quantum computers up on the cloud, the people in the field were either working on whiteboards or they were building their own devices in the lab, right? And neither one was particularly computationally sophisticated. So on average, physicists over a certain age don't really program. It was one of the weird things for me, because I come from obviously from more of an IT background, right? So this was the first time I've hung out with so many PhDs in physics. And I was surprised, because I mean, I guess my bias is like, well, if you're building stuff, you're going to be writing code, right? Like, no, they were building their own devices on lab tables, or they were just writing equations on whiteboards, and that was their output was equations. So the younger the physics PhD that I've run into, the more likely it is that they were taking a computational approach from very early on. And I see them as really an accelerator for the field itself, because right now, most of the people in sort of the peak of their career or leading teams or whatever are not that good at code. So, it's funny, because I'm bringing a bunch of friends into the quantum team who don't have a physics background, who don't have a quantum background, or quantum information background. What they have is a modern cloud application architecture and high level languages and streams processing and all these sort of concepts that have really gotten honed over the last 5 to 10 years of building massive internet-based or cloud-based applications and mobile applications. And they're taking these physicists to school and saying, like, what you've built here, I mean, Qiskit's got some major flaws in its architected, and this goes back to the re-architecting of how, or the repackaging of the abstraction, right? Like, it's again sort of analogous to data science, because that's the starting place for data science is Python in a notebook, but nobody runs a production application out of a Jupyter notebook, right? You build your model and then you figure out how to deploy it into your production application. They hadn't really figured out that was they were going to have to do someday, right? Because they were thinking, well, we'll just run in Python forever. We're like, we have some really bad news for you. Like, so if you're coming at this right from the get-go with computational approach to physics and CS and information science grounding, then you've got an advantage for sure. I mean, I think that, like I said, I think this younger generation that are in the sort of freshly minted PhDs have a higher probability of having a computational approach, and in many ways they are more comfortable with where quantum computing is right now than the sort of the more senior people.
Okay, so would you say then it would be better to be quantum focused with a computational background, or computational focused with or I should say, physics focused with a computational
Yeah.
background. Or
It's up to you.
quantum,
I mean, I think
background.
either one would be perfectly fine. It really depends on what you're more motivated by. Like if you wake up in the morning thinking about algorithms, then do CS with a physics flavor. And if you think about like math equations, then do physics with a CS side, right? I mean, it's really what motivates you. I mean, there's plenty of opportunity for both.
Okay, thank you.
Sure. I should probably wrap up because I haven't had dinner and I need to go grab some food.
Yeah, I was just gonna ask real quick one last time if anybody
Sure.
else had any questions to ask.
I'm gonna ask you about that Google master's program at some point. So
UCLA, yeah.
Oh, what did I say?
Google.
Google.
Wow,
You're gonna get a degree at Google University.
That's what most people get their degrees. That's where my medical degree comes from.
Oh no.
WebMD.
I mean,
I'm not a
Google's
doctor, but I
certification
can
program.
Google things.
Stack Overflow, but for ailments.
I'm gonna Google the UCLA master's program. How
Well, it doesn't exist yet, Ben. So if you're interested, I can connect you with Eric Hudson is the UCLA prof who's closest to the planning, and I'm sure he'd be interested in getting your viewpoint. Actually, I mean, he's sort of trying to get a sense of what the level of demand and what people would want from these types of programs. So I'll connect you.
Was it 23? I think I looked it up at some point.
Sorry?
Was it 2023? You said they were going to.
I can't remember exactly. I think it is, but I'm not certain. I think that was the first semester they were planning on having it.
Gotcha. Oh, okay. Let's see. Establishing an interdisciplinary program that's set to begin in fall of 2022.
Oh, okay. They
really
moved it up a year, or I misremembered.
Yeah. Well,
anyway, I will follow up with the slides. And if anybody on the call wants to contact me for follow-up questions, Ishan and Andrew both have my email address, probably others on that copied on an email, maybe you, Thomas, I'm not sure. But anyway, feel free to send my email address out to anybody who wants it.
All right. Thank you so much, Sebastian, for coming here and talking with us. That was extremely useful, and you had a lot of insights to add.
Good.
One more quick thing.
Yes.
Could you maybe link your LinkedIn in chat so that if anyone wants to
that's a good idea.
you, that they could?
Absolutely. Let me do that right now.
Awesome.
Talk amongst yourselves.
I'm going to go ahead and stop the recording.
oh yeah,
Good idea.